Next, we're going to talk about dividing radicals. We can use conjugates to rationalize denominators with binomial denominators. Notice that 1 over the square root of 5 minus 1 is not simplified because there's a radical in the denominator. Now, we have rationalized denominators with only monomials before, and all you needed to do is multiply the needed values to get the radicals expression to become integer expressions. So for example, 1 over the square root of 5. Notice that this denominator is a monomial, meaning there's no pluses or minuses in the bottom. Now we've actually already done this before. You just multiply by some radical so that you get a result that comes out of the denominator. I have 1 square root of 5, but in order for it to come out of the house, I need 2 copies. So how many more copies do you need? Well, just 1 more. If you multiply it to the denominator, you also then multiply it to the numerator. So let's take a look at this denominator more carefully. The square root of 5 times 5, the 2 5s get to go out of the house, and you have nothing left inside the house. So we've successfully made this monomial radical in the denominator to be an integer. So then I finish up the top by multiplying by the square root of 5, and I get the square root of 5 divided by 5. Now, clearly this method for rationalizing monomial radicals in the denominator won't work for binomial radicals in the denominator. With a binomial denominator in the radicals, we need to rationalize a different way. And the different way is to multiply by the conjugate of the denominator. To be clear, let's look at the binomial denominator 1 over the square root of 5 minus 1. If I just multiply by the missing value, root 5, like I did with the monomials, okay? So this is a binomial. So if I try to use the same method, it won't work. Let me show you what happens. When I distribute here, I get the square root of 5 times 5, and that comes out of the house, but then I get minus the square root of 5. So in the denominator, I still have the 5 comes out of the house, and minus root 5. Now, I haven't done the numerator yet, but it doesn't really matter at this point. I still have a radical in the bottom. So the method that we use for monomials isn't gonna work for binomials. But we can rationalize the denominator with binomials in the denominator by multiplying by the conjugate. Remember when we multiplied by the conjugate on the last page? It turned out to be a whole number in the bottom without radicals. So we're going to do the same thing to divide. So I need to rationalize the denominator because we have a radical in the denominator, and that's not okay. I'm going to be multiplying by something clever here. And the clever thing that we're going to choose is the conjugate. So I'm going to multiply by the square root of 5 plus 1. Whatever you do to the denominator, you will also have to do to the numerator. So now I distribute these, and I'm getting the square root of 5 times 5 plus the square root of 5 minus the square root of 5 minus 1. So the 2 squares of 5 add to 0, and then I'm just left with, this comes out of the house, it's 5 minus 1, or just 4. Yay, I have successfully got the denominator to not have a radical. So then I'm going to go back to the numerator and finish that. So that gets me root 5 plus 1, which comes down all the way. Now, this is my final answer. We know it is reduced completely because you have no more radicals in the denominator. It's only in the numerator, which is fine. On our next problem, we have another binomial in the denominator. I have lots of radicals in the denominator, and I have to get rid of them. So I'm going to be multiplying by something clever, and the clever thing that we've chosen to multiply by is the conjugate. So the conjugate of the square root of 6 plus 2 is the square root of 6 minus the square root of 2. And then I can distribute like we did on the previous problem. But do you remember when we used the difference of squares? I can probably do this a little bit faster knowing that when two conjugates multiply, I know I get a squared minus b squared, where a in this case is the square root of 6, minus, because the formula says so, the square root of 2 squared, which gets me 6 minus 2, which is 4. So I can use that formula, the difference of two squares, so that I can get my answer a little bit quicker in the denominator. If you don't like that, if you're like, I'm never going to remember that, that's okay. Do it the long way like I did on the first problem. When I distribute, I get the square root of 18 minus the square root of 6. It looks like 18 can probably reduce here. Let's try that. It can, so we get 3 times the square roots of 2. 6 is just 2 times 3, which does not reduce. So that all comes down. If I could factor anything out of the numerator, the coefficients, I would, so that I could try to reduce, but in this case I can't. So I am fully reduced. On our next problem, again we have a binomial in the denominator, and because I have a binomial with radicals, I need to rationalize the denominator with a conjugate. So I'm going to multiply by the conjugate of the denominator. Sometimes students, when they see this numerator here, they want to multiply by the conjugate of the numerator. But remember, the only thing that is a problem is that there's radicals in the denominator. We are allowed to have radicals in the numerator. That doesn't really matter. The only thing I'm really trying to take care of is that there's no radicals in the denominator. So when I distribute this, I'm going to use the shortcut here, a squared minus b squared. So the square root of 6 squared minus the square root of 8 squared, just so I don't have to write out the two middle terms, which I know are going to reduce. We have the square root of 6 squared, that's just 6. The square root of 8 squared, that's just 8. And then I'm going to subtract them and get negative 2. Now that I've successfully got the denominator to not have a radical, now I'm going to go back and distribute my numerator. There's no shortcuts on this because they aren't conjugates, so you can't use the difference of squares. So we have the square root of 48 plus the square root of 64 minus the square root of 12 minus the square root of 16. It looks like a lot of those are going to reduce. 48, let's try that one. Now we know 4 and 4 could go down again, but all I'm looking for is groups of 2. So I found a group of 2, so let's just go ahead and take it out. If you broke it down more, it's still going to come out the same. The square root of 64, that's a perfect square. 8. 12 looks like it breaks down. That's going to be minus 2 times the square root of 3. And 16 is a perfect square. So now I can combine like terms. In my numbers, I have 8 and minus 4. That's positive 4. We have the same radicand under the root, which means I need to add or subtract my coefficients, in this case plus 2 square roots of 3. You could have put that in the other order, 2 square roots of 3 plus 4. Either way is going to work. Now, like I said in the last problem, if I can reduce, I would need to reduce. The last one didn't reduce, but this one does. Notice that the coefficients in the numerator, 2 and 4, can factor out a 2. And I have 2 plus 1 square root of 3. Notice that when I factored out the 2, I only factored it out of the coefficients, not the radicals, because there's only a radical in 1, not in 2. And then look what happens here. 2 divided by negative 2, that's negative 1, times 2 plus the square root of 3. This is my final answer. If you want to distribute your negative through, you're welcome to. So another acceptable answer would be negative 2 minus the square root of 3. These are both acceptable. On our last problem, again we have a binomial in the denominator with radicals. The only way to get rid of a binomial with radicals in the denominator, to rationalize it, is to multiply by its conjugate. So the conjugate of the square root of 3x plus the square root of 5y is the square root of 3x minus the square root of 5y. Whatever you do to the denominator, you must also do to the numerator. Yes, there is a binomial with radicals in the numerator, but again, we're allowed to have that. So don't make the mistake of trying to take the conjugate of the numerator. That's totally fine. We are allowed to have that. In the denominator, I'm going to use my shortcut a squared minus b squared. I know that a is the square root of 3x, and I know that b is the square root of 5y. And when I reduce, in the denominator, it looks like I have just 3x minus, because there's a minus in the formula, the square root and the square undo each other, and that gives me 5y. So now I have successfully got the denominator to not have any radicals in it. So to finish this problem, I need to go back to the numerator and distribute, which is going to get me the square root of 6x squared. Notice I can't use any shortcuts because this is not a conjugate, so I have to do it the long way. Minus the square root of 10xy minus the square root of 3xy minus, plus, a negative times a negative is a positive, the square root of 5y squared. So it looks like some of these are going to reduce. 6x squared, 6 can break out on 2 and a 3, but that's not a pair. But x and x is a pair. So the x comes out and the root 6 stayed home. Both the 2 and the 3 stay home and multiply. In 10xy, we have 2 and 5 and x and y, no pairs. In 3xy, again, no pairs. In 5y squared, well, that's 5y times y. So the y gets to come out, and the 5 stays inside. Now, a common student mistake is that you want to add these two things together in the middle, the 10xy and the 3xy, because clearly their variables are the same. But remember, in radicals, the entire radicand has to be the same. So 10xy is not the same thing as 3xy, so you can't reduce those. So this is my final answer. X times the square root of 6 minus the square root of 10xy minus the square root of 3xy plus y root 5 all over 3x minus 5y. And that concludes this lesson.